Good afternoon all. Welcome to the lecture of discrete mathematical structure. Okay, so in last lecture we have seen what is an adjoint of a matrix. After that we have defined inverse of a matrix. When the inverse of a matrix will be exist if the matrix will be a non-singular matrix. That is a necessary and sufficient condition for any square matrix of order n to be invertible is that it must be a non-singular matrix. Then only the corresponding matrix. Then we see that the corresponding matrix will be a invertible matrix. Otherwise it is not. Okay, and any invertible matrix is also called as non-singular matrix, and if determinant of P will be equal to 0, then the matrix is called as a singular matrix. Okay, now we will see some properties of inverse of a matrix. Screen is visible. Is the screen is visible? Okay. Okay. So now first will be the inverse of a matrix is unique. Of a matrix is unique. That is, if A be any matrix, then if it is invertible, then its inverse matrix must be a unique. What is the inverse of a matrix? If suppose A be a square matrix of order n, then there exists one another matrix B of same order, that is of order n, such that A into B equal to B into A equal to I. Then we say that the matrix B is the inverse of a matrix A. So such a inverse is unique. That is we have to prove. Okay. So if possible, let us take solution will be, if possible, suppose that the matrix A has two inverse. Matrix A has two inverses B and C. Inverses B and C. And by the definition of inverse of a matrix, as B is the inverse of a matrix A, which implies A into B equal to B into A, which is equal to identity matrix. Similarly, C is also inverse of A, which implies A into C equal to C into A equal to identity matrix. Take this one as equation 1, this one as equation 2. Now, pre-multiplying both sides of equation 1 by matrix C, we get pre-multiplying 1 by A, we get C into AB is equal to C into PA is equal to R. Okay. Now consider this CAB. CAB can be written as C into matrix A into B. Since matrix multiplication is associated, therefore we can write C into AB as C into AB, which is equal to C into A into B from equation 1. A into B is equal to I, and C into I, that is any matrix with multiplication of any matrix with identity matrix is nothing but the matrix itself, that is C. And CAB equal to C into A. Again, matrix multiplication is associated. Therefore, CAB can be written as CA into B. That is CA into A. That from equation 2. C into A is I into B, which is equal to B. Now, for equation 3 and equation 4, okay, C into AB is equal to C and C into AB equal to B. As the LHS is same, then RHS must be same. Since here LHS is equal, that is equation 3 and 4. LHS has same value, CAB. And RHS is nothing but C into B. As LHS is equal, then RHS must be equal, which implies C equal to B. So here we have taken two inverses of a matrix A, that is B and C. But after solving some step, here we get C equal to B. Therefore, from this we say that if inverse of a matrix exists, then it must be unique. Since here we have taken two different inverses, but after solving some steps, we get B equal to C. From that, we say that the inverse of a matrix is always unique. the inverse of matrix is unique. Now, second one, A into B inverse is equal to B inverse into A inverse. Okay, so here we have to check A into matrix A into B inverse is nothing but B inverse into A inverse. Okay, now let A and B are two matrices. Let capital A and B are two non-singular matrices, means they are invertible matrices. Non-singular matrix. Since as here there exists an inverse, then they must be a non-singular matrices only. Since if the matrix is singular, then it is not invertible. Okay. Now, as A and B are two non-singular matrices, then the inverse of these two matrices should be exist. Okay. So here we have to prove that A into B inverse, A into B inverse is nothing but B inverse into A inverse. That is, inverse of a matrix A into B is nothing but B inverse into A inverse. So consider B inverse into A inverse into matrix A into B is equal to, as we have to show that matrix A into B has an inverse, B inverse into A inverse, then we have to show that product of A into B inverse into A inverse equal to A inverse in B inverse into A inverse into AB is equal to I. So here we have considered B inverse into A inverse into AB, but we know that matrix multiplication is associative, therefore we can write this one as a B inverse into A inverse into A into B, which is equal to B inverse into, as here A and B are two non-singular matrices, which implies they are invertible. As A is invertible, then A into A inverse will be equal to I. Therefore, its value is I into B. But I into anything is that the remaining anything value, that is B inverse into B, and B inverse into B will be equal to I. Similarly, A into B into B inverse into A inverse, which can be written as A into B inverse into A inverse, which is equal to A into B into B inverse I into A inverse, which is nothing but A into A inverse, and which is equal to I. Therefore, here we have proved that B inverse into A inverse into AB equal to I, and AB into B inverse into A inverse, which is again I. Therefore, from this we say that inverse of a matrix AB is nothing but B inverse into A inverse, and inverse of a matrix A into B is denoted by A into B inverse, and inverse of this matrix is B inverse into A inverse, and that is we have to. Hence, AB inverse is nothing but B inverse into A inverse. Okay, now we can extend this method on any number of matrices. For example, if suppose we have some K matrices, that is inverse of A, B, C up to so on K inverse is nothing but K inverse up to so on C inverse into B inverse into A inverse. That is, if there are any number of invertible matrices, then product of that its inverse is nothing but inverse of K inverse into whatever will be its second term up to so on C inverse, B inverse up to A inverse. Okay, so in this way we can find out the inverse of a product of matrices. Now, third property will be the inverse of a transpose of a matrix, transpose of a matrix is the transpose of the inverse. Transpose of the inverse of a matrix. Inverse of a matrix. Okay. So here we have to show that inverse, that is actually we have to show that here inverse of a transpose of a matrix. If suppose A be a matrix, then its transpose will be A dash, and its inverse is nothing but transpose of the inverse of a matrix. Inverse of a matrix is denoted by A inverse and its transpose. That is we have to prove. A transpose inverse is nothing but A inverse transpose is we have to show. Okay, see its solution. Now, let A be a non-singular matrix. A be a non-singular matrix. Non-singular matrix. As A is non-singular matrix, which implies A is invertible. As A is invertible, then it means that determinant of A is not equal to 0. as determinant of A is not equal to 0, and we know that determinant of A and determinant of A transpose is same. Therefore, as determinant of A is not equal to 0, which implies determinant of A transpose is also not equal to 0, since determinant of A is equal to determinant of A transpose. Okay. Now, as A is an invertible matrix, then by definition, A into A inverse equal to A inverse into A equal to I, which is from the definition of inverse of a matrix. Inverse of a matrix. Okay. Now, taking the transpose on each side of this equation, then we get A into A inverse transpose equal to A inverse into A transpose equal to I transpose. Okay. And we know that A into B inverse, A into B transpose is nothing but B transpose into A transpose. So this one is nothing but A inverse transpose into A transpose is equal to A transpose into A inverse transpose, and identity transpose of invertible identity matrix is identity only, and this is from A into B transpose is nothing but B transpose into A transpose. Okay. Now, so here A inverse transpose equal to A transpose, sorry, A inverse transpose into A transpose is equal to A transpose into A inverse transpose is equal to I. Then by definition of inverse of a matrix, as A into B equal to B into A equal to I, then we say that the B is the inverse of A. As here B is equal to A inverse, take B equal to A inverse, then A into B equal to B into A equal to I, which implies inverse of this transpose of a matrix is nothing but A inverse of transpose. Okay. So this one is the required result. This one is inverse. This will be a transpose, that is T, and this one is a inverse of, actually can write this one as a, this one is a, actually our A, okay. Then by definition of inverse of it, consider this one as A, this one as B. So this one is A and this one is B. So B into A equal to A into B equal to I. Then inverse of a matrix A is nothing but B. So A transpose inverse is nothing but this matrix, that is A inverse transpose. Okay. And that is we have to show, that is inverse of a transpose of a matrix is nothing but the transpose of a inverse of a matrix. Okay. Kunal, काही doubt? कुणाला काही डाऊट आहे का?
No, sir.
Okay, now find the adjoint of examples. First one, find the adjoint of matrix A and of matrix A whose entries are 4, 2, -1, 3. Okay, and how to find out adjoint of a matrix? Actually, adjoint of a matrix A is nothing but, first we have to convert this matrix into a determinant, and then its adjoint is nothing but we have to find out the cofactor of the each element of the matrix, and transpose of that cofactor matrix is nothing but the adjoint of a matrix A. Okay, as here A is equal to, matrix A is nothing but 4, 2, -1, 3. Then its transpose is nothing, sorry, its determinant is nothing but 4, 2, -1, 3. Okay, now we have to find out the cofactor of the each element of the matrix, that is each element of the determinant of A. This one is A11, A11, this one is A12, this is A21, and this is A22. Now we have to find out the cofactor of A11. Cofactor of A11, and which is denoted by capital A11. Cofactor of A11, which is denoted by capital A11, and which is nothing but minus 1 to the power 1 plus 1. That is, cofactor of the element Aij is nothing but minus 1 to the power I plus j into its minor. Okay, so minus 1 to the power 1 plus 1, 1 plus 1, which is 2, minus 1 square is plus 1. Plus 1 into minor of this. Minor is nothing but we have to suppress the row and column in which the element present. As A11 will be equal to 4, then we have to suppress the first row and first column. Then minor is 3. So 1 into 3 is 3. Similarly, cofactor of A12. Cofactor of A12, which is denoted by capital A12, minus 1 to the power I plus j, 1 plus 2 into its minor. Now, A12 is an element which is present in the first row and second column, that is element 2. Suppress the row and column in which the element present, that is first row and second column, then its minor will be minus 1. And this minus 1 to the power 1 plus 2 is minus 1 into minus 1, which is equal to plus 1. Minus 1 into minus 1 plus 1. Now, cofactor of the element A21, which is denoted by capital A21, and which is equal to minus 1 to the power 2 plus 1 into its minus, which is 2, and which is equal to minus 1 into 2 minus of 2. Similarly, cofactor of the element A22 equal to, which is denoted by A22 minus 1 to the power 2 plus 2, and its cofactor is nothing but 4, which is equal to minus 1 to the power 2 plus 2, which is 4, which is an positive number, and into 4. Okay, so these are the cofactors of the elements of determinant of A. Now we have to find out the cofactor matrix. Therefore, the cofactor matrix is A11, A12, A21, A22, and which is equal to A11 is nothing but 3, A12 is 1, A21 is minus 2, and A22 is 4. Okay, so this will be the cofactor matrix of a given matrix, as this one is matrix, which is denoted by the symbol of matrix. Okay, one minute. Okay, now this one is the cofactor matrix. Okay, but we have to find out the adjoint of a matrix, and adjoint of a matrix is denoted by this symbol, and adjoint of a matrix A is nothing but transpose of a cofactor matrix. Transpose of a cofactor matrix. Okay, now our cofactor matrix will be this one. Now we have to just take its transpose. And what is a transpose of a matrix? We have to make the rows as columns and columns as rows. Therefore, the first row is nothing but the first column, and the second row is nothing but the second column. And similarly, we get the first column as a first row and the second column as a second row. So this will be the adjoint of a matrix A, and having entries will be 3 minus 2 1 4. In this way we can find out the adjoint of any matrix of a given order. Now find out the inverse of a matrix by using the adjoint method. So take second example as find the inverse of a matrix find the inverse of a matrix having entries are 1 2 3 1 2 3 1 3 3 and 1 2 4. Okay, so we have this matrix and we have to find out its inverse, and we know that inverse of a matrix can be find out by, we know that inverse of a matrix A is nothing but 1 upon determinant of A into adjoint of a matrix A. So for the inverse of a given matrix we require determinant of A and adjoint of a given matrix A. So let A be a matrix which is given equal to our given matrix 1 2 3 1 3 3 1 2 4. Now it first find out its determinant, which implies determinant of A is equal to 1 2 3 1 3 3 and 1 2 4. Okay, now its determinant can be calculated as 1 into its minor, that is 4 into 3 12 minus 6 minus of 2 into 4 minus 3 plus 3 into 2 minus 3, and which is equal to 12 minus 6 6 minus of 2 into 4 minus 3 will be 1 plus 3 into 2 minus 3 is minus 1, which is equal to 6 minus 2 minus 3, which is equal to 6 minus 2 minus 3 minus 1, and which is equal to 1, and 1 is not equal to 0, which implies determinant of A is not equal to 0. So the given matrix A is invertible. So the given matrix capital A is invertible. Now we have to find out its inverse, and for that we require adjoint of a matrix A. So to find out the adjoint of a matrix A, we have to first find out the cofactor matrix of the given matrix, and its transpose is nothing but the adjoint of a matrix A. So as A equal to 1 2 3 1 3 3 and 1 2 4, then we will find out the cofactor of the each element of the given determinant. Okay, now the cofactors are now first cofactor will be A11, and which is nothing but minus 1 to the power 1 plus 1 into its minor, and A11's minor is nothing but 3 3 2 4, which is equal to minus 1 to the power 1 plus 1, which is plus 1, and its determinant will be 4 into 3 12 minus 6 12 minus 6, and which is equal to 6. So A11 equal to 6. A12 is equal to minus 1 to the power 1 plus 2 and its minor. A12 is present in first row and second column, then it is nothing but 1 3 1 4, and which is equal to 4 minus 3 and minus 1 to the power 1 plus 2 will be minus 1 into 4 minus 3, and which is equal to minus 1 into plus 1, and its value will be minus of 1. Again, A13 is the element which is present in the first row and third column, so its cofactor will be minus 1 to the power 1 plus 3 into its minor. Its minor is 1 3 1 2 1 3 1 2, which is equal to minus of 1 to the power 1 plus 3, which is 4, and its negative powers negative terms even power will be plus, and it is nothing but 1 into 2 minus 3, which is equal to 1 into minus 1, and it's minus 1. 6 minus 1 minus 1 are the first entries. Now 8 to 1 is equal to minus 1 to the power 2 plus 1 into its minors A21, 2, 3, 2, 4. So which is equal to minus 1 to the power 2 plus 1, which is 3, minus 1 to the power 3 minus 1 into 4 into 2, 8, minus 3 into 2, 6, which is equal to minus 1 into 2, which is equal to minus 2. Similarly, A22 is equal to minus 1 to the power 2 plus 2 into 1314, and which is equal to minus 1 to the power e1, which is plus 1 into 4 minus 3, and which is equal to 1 into 1, and its value will be 1. Similarly, A23 is equal to minus 1 to the power 2 plus 3 into 1212, which is equal to minus 1 into 2 minus 2, and anything into 0 will be 0. Now A31 is equal to minus 1 to the power 3 plus 1, 2, 3, 3, 3, which is equal to minus 1 to the power plus 4, which is 1, 2 into 3, 6, minus 9, 6 minus 9, minus of 3. A32 is equal to minus 1 to the power 3 plus 2 into A32, 1313, 1313, minus 1 to the power 5 minus 1 into 0, since 3 minus 3, which is 0. Now A33, last cofactor term will be minus 1 to the power 3 plus 3 into 1213, 1213, minus 1 to the power 3 plus 3 plus 1, 3 into 1, 3 minus 2, which is equal to 1. So here we get the transpose of cofactor of the each element of the given matrix. So the transpose, so the cofactor matrix is is A11, A12, A13, A21, A22, A23, A31, A32, and A33. Now just put out its value. Now A11, A12, A13, A11, A12, A13, 6 minus 1 minus 1. Put its value 6 minus 1 minus 1. A22, A22, sorry, A21, A22, A23, and its values are minus 2, 1, 0, minus 2, 1, 0, and A31, A32, A33 are minus 3, 0, 1, minus 3, 0, 1. So this will be the cofactor matrix of a given matrix. Now we have to find out its transpose. This we have to find out its adjoint. Adjoint of a matrix A is nothing but transpose of this matrix, cofactor of a matrix. Transpose of cofactor matrix 6 minus 1 minus 1, minus 2, 1, 0, minus 3, 0, 1. Take its transpose, we get adjoint of a matrix A as 6 minus 2 minus 3, minus 1, 1, 0, minus 1, 0, 1. Okay, 6 minus 2 minus 3, minus 1, 1, 0, and minus 1, 0, 1. So this will be the adjoint of a matrix. So here we get the adjoint of a matrix. Now we have to find out its inverse, and as A inverse is nothing but 1 upon determinant of A into adjoint of A, which is equal to 1 divided by determinant of a given matrix. We have find out the determinant of given matrix, and which is I think 1, that is this one is. So here we get the determinant as 1 into its cofactor matrix, that is adjoint matrix, and which is 6 minus 2 minus 3, minus 1, 1, 0, minus 1, 0, 1. And from this 1 divided by 1 will be 1. So its product will be 6 minus 2 minus 3, minus 1, 1, 0, minus 1, 0, 1. And that will be the inverse of a given matrix. matrix A. So in this way, we can find out the inverse of any non-singular matrix by using the adjoint of a matrix. Okay, Kunal, काही doubt?
No.
Okay. Now, the next concept will be the solution of a system of linear equations by matrix method. Okay, so here we have to see the method to find out a solution of a given system of linear equations. Okay, what the linear equations are nothing but the linear equations are of the type ax plus by equal to c. Such equations are called the linear equations, and if we have two or more than two linear equations and we have to find out its solution, then we can use the matrix method. Okay, now first one, two equations. First we will see the what is the homogeneous and non-homogeneous system of linear equations. So first one, non-homogeneous system of linear equations. Okay, so two equations with two unknowns. Here we have to see we have to take two equations and there are only two unknowns in that equation. That is, first one is ax plus by is equal to some d or some c, or we can take this one as a a1x plus b1y equal to c1. a1x plus b1y is equal to c1, and a2x plus b2y is equal to c2. So these are the two equations with two unknowns, that is x and y are unknowns. Here we have to find out these values of x and y, and a1 b1 c1 a2 b2 c2 are any arbitrary constant. Okay, so these are the two equations with two unknowns, and these two equations can be written in the matrix form as these two equations can be written in a matrix form as this way: a1 b1 a2 b2, which is into xy, and which is equal to c1 c2. So the given system of linear equations can be written in a matrix form. That is, this one is nothing but a1 into x plus b1 into y, which is equal to c1, a2 into x plus b2 into y, which is equal to c2. Therefore, this one is nothing but the this one. Let us take this one as ax equal to b, where matrix A is nothing but a1 b1 a2 b2. Capital X is nothing but a 2 by 1 matrix, that is x y, and matrix B is nothing but c1 c2, which is again a 2 by 1 matrix. That is, there are two rows and two columns in both the matrices x and b, and this one is a square matrix of order 2. This is for the two equations and two unknowns. If suppose we have three equations and three unknowns, three equations and three unknowns, three unknowns, and these are nothing but a1x plus b1y plus c1z is equal to d1, a2x plus b2y plus c2z equal to d2. Similarly, a3x plus b3y plus c3z is equal to d3. So this one will be the three equations with three unknowns. The unknowns are x, y, and z. Again, this can be written in matrix form as matrix form as the matrix which contains three rows and three columns, A1 B1 C1, A2 B2 C2, A3 B3 C3 into a matrix of unknowns X Y Z equal to the arbitrary constants D1 D2 and D3, where these D1 D2 D3 are maybe 0 or may not be 0. Okay, as these are non-zero, non-homogeneous, then these d1 d2 d3 are not equal to 0, where this one is nothing but ax plus equal to b, where a is a matrix of order 3 cross 3, this one is a, this one is x, and this one is b. Okay, so if we have any system of linear equations with same number of equations and same number of unknowns, then we can write in the form of ax equal to b. Okay, now when the solution of this given system of linear equations will be exist. Okay, now if suppose a is a non-singular matrix, if a is non-singular, that is determinant of a is not equal to 0. If a is non-singular, then pre-multiplying both side of ax equal to b by a inverse we get. Okay, if our matrix A is non-singular, then we have to just multiply both sides of this equation by a inverse, then we get a inverse into ax is equal to a inverse into b. But matrix multiplication is associative, therefore this one is nothing but a inverse into a into x, which is equal to a inverse into b, and a inverse into a is I into x equal to a inverse into b, and which implies x is equal to a inverse into b. So if the matrix is non-singular matrix, then the solution of that given system of linear equation is obtained by just taking x as equal to a inverse into b, and we can find out this a inverse by using the adjoint method, and we have to just multiply this by a matrix b, then we get the values of this x, that is the x contains, if it has 3 equations and 3 unknowns, then values of x y z will be get from this one. So in this way we can find out the solution of given system of linear equation by using the inverse of a matrix, where if it is a non-singular matrix. Okay, now consistency and inconsistency of a system of linear equation. System of linear equations. First we will see when the given system of linear equations are consistent and when they are inconsistent. Okay, the given system of linear equation is said to be consistent if it has a one or more solution. That is, if it has a solution, they are consistent. Otherwise, they are called as a inconsistent. Okay, so definition will be the given system of linear equation or given system of equations are consistent if they have one or more solution. They have one or more solutions and are called or are said to be inconsistent if they have no solution. Okay, so a given system of linear equation is said to be consistent system of linear equation if it has a solution, and if it has no solution, then the given system of linear equation is said to be inconsistent. Now we will see how to check whether the given system has a solution or not. In that first one, if determinant of A is not equal to 0, then the given system has solution, then the given system is consistent and it has unique solution. Given system is consistent and it has unique solution. It has unique solution whenever the determinant of A is not equal to 0. That is, the given matrix is a non-singular matrix. And if determinant of A is equal to 0, if determinant of A will be equal to 0, then the given system has system has either a no solution, either a no solution or infinite number of solutions, infinite number of solution. Okay, so if determinant of a is equal to 0, then the given system has either no solution, that is the solution not exist, or it has, if it exists, then it has infinite number of solution. Now how to check whether the given system has a solution or it has infinite number of solution? Okay, for that, find out adjoint of A into B when it is, whenever determinant of A is equal to 0. Now in that, if adjoint of A into B is not equal to 0, then the given system has no solution. Then the given system has no solution. Okay, if suppose determinant of A is not equal to 0, then the given system has unique solution and it is consistent. And if suppose determinant of A equal to 0, then there are two possibilities, either it has a no solution or it has infinite number of solution. And how will you check this one? First we have to find out the adjoint of A into B. If adjoint of matrix A into B is not equal to 0, then the given system has no solution. And if it is equal to 0, if adjoint of A is equal to 0 into B is equal to 0, then the given system has infinite number of solution. Given system has infinite number of solutions. Number of solutions. So in this way we can check whether the given system is consistent or inconsistent, and from that we can also check whether it has a unique solution, no solution, or infinite number of solution. This is for the non-homogeneous system of linear equations. Now see what is the homogeneous system of linear equations. Homogeneous system of linear equations. Okay, so what is a homogeneous system of linear equations? Just it is same as a non-homogeneous system of linear equations, but the RHS in the non-homogeneous system of linear equation is 0, then it becomes the homogeneous system of linear equations. In that, first see two equations with two unknowns. Equations with two unknowns. Okay, that is, this one is in the form of a1x plus b1y equal to 0 and a2x plus b2y equal to 0. Such equation, such system of equation is called as a homogeneous system of linear equation, since its RHS value will be always 0, and it can be written in matrix form as, a1 b1 a2 b2 into xy is equal to 0 0. Okay, this RHS in the homogeneous system of linear equation is always 0. Okay, so and it can be written in matrix form in this way. And if suppose it has a 3 equations and 3 unknowns, that is a1x plus b1y plus c1z equal to d1 and a2x plus b2y plus c2z equal to d2 and a3x plus b3y plus c3z equal to d3. Again it can be written in a matrix form as a1 b1 c1 a2 b2 c2 a3 b3 c3 into x y z into d1 d2 d3, sorry, equal to d1 d2 d3. So any system of linear equations can be written in matrix form in this way, that is ax equal to b, where a is a matrix of order 3 by 3, x is a matrix of order 3 by 1, and b is also a matrix of order 3 by 1. As here this one is a homogeneous system of linear equation, then here the values of d1 d2 and d3 are equal to 0. So take this d1 d2 d3 as a 0, and here matrix B is nothing but the 0 matrix of order 3 by 1, that is denoted by O. Okay, Now, if suppose A is a non-singular matrix, that is determinant of A is not equal to 0. If determinant of A is not equal to 0, then multiply this equation Ax equal to 0 by multiply Ax equal to 0 by A inverse. That is pre-multiply. We get A inverse into Ax is equal to A inverse into 0 matrix. A inverse into A, I into X is equal to anything into 0 will be 0, and which implies X equal to 0. So if this given system, given matrix is non-singular matrix, then the given system has only one solution, which is X equal to 0, and such a solution is called as a trivial solution. Okay, see what is a trivial solution. Okay, if x1 equal to x2 equal to 0 in the homogeneous system of two equations with two unknowns, that is if x1 equal to x2 equal to 0 is called a trivial solution of a1x plus b1y a1x1 is called trivial solution if a1x1 plus a2x2 is equal to 0 and b1x1 plus b2x2 is equal to 0. Since whatever will be the values of a1, a2, b1 and b2, as x1 and x2 equal to 0, then it holds always this condition. That is x1 into anything will be 0 since x1 equal to 0. Similarly x2 into a2, as x2 is 0, then a2 into that 0 will be 0. Therefore this always holds these conditions. Therefore such solution is called a trivial solution. Similarly, if there are three equations and three unknowns, then if the value x1 equal to x2 equal to x3 equal to 0, x1 equal to x2 equal to x3 equal to 0 is called a trivial solution of homogeneous system of linear equations a1 x1 plus b1 y1 plus c1 z1 equal to 0. Here actually we have to take x1 x2 x3 x1 x2 x3 x1 plus b2 x2 plus b3 x3 and which is equal to 0. I think there is a small mistake. b2 x2 into c2 x3. Similarly a3 x1 plus b3 x2 plus c3 x3. Again here, whatever will be the values of a1, b1, c1, a2, b2, c2 and a3, b3, c3, as x1, x2, x3 is equal to 0, then always LHS is equal to RHS. Therefore, this one is always a solution of the given system of linear equations, that is homogeneous system of linear equations. As x1, x2, x3 equal to 0, that is if it has a three equations and three unknowns, then this one will be a solution. Whatever will be the system of linear equations, or that is homogeneous system of linear equation, it has always a solution which is a trivial solution. The trivial solution is always a solution of the homogeneous system of linear equation. Always a solution of the homogeneous system of linear equations. System of linear equations. Okay, it implies that homogeneous system is always consistent. Homogeneous system of linear equations are always consistent. Equations are always consistent. Since it has always a solution and it is a trivial solution. Always consistent. And if we have to find out its non-trivial solution, then for that we make the given matrix as a singular matrix. If the given matrix A is a singular matrix, then it has only a unique solution and it is a trivial solution. And if we have to find out its non-trivial solutions, then for that we require our given matrix is a singular matrix. Then only it is possible that it has a non-trivial solution. Otherwise, the non-singular matrix has only a trivial solution. Okay, Kunal, kind out?
No, sir.